And now it is my distinct pleasure to introduce our first speaker. Sydney Anderson is a pre-medicine major from Dublin, Ohio, and she decided UD was the right place for her because of our close community, our opportunities for impactful service, and last but not least, because of the rigorous academics that we cultivate here. Sydney has been working in the lab of Dr. Marjorie Kango Singh, where she has been studying fruit flies in order to better understand the causes of colorectal cancer. This kind of research, I've got to say, with this kind of research with real-life impacts, I've got to say is a real hallmark of the kind of the approach to education and the generation of new knowledge that we have here at UD. Beyond her work with Dr. Kango Singh's lab, Sydney is also part of an a cappella group, the Flying Solos. I don't know if they're here. And she's also been serving in the University of Dayton Emergency Medical Service for the past 3 years. Eventually, Sydney hopes to be a doctor, and she really wants to advocate for patient education and furthering community health. And she's taken one big step in this direction this coming fall when she will be attending the Ohio State College of Medicine in Columbus, Ohio. And just yesterday, right? I think she learned yesterday that she's actually gotten a scholarship, the Dr. Joel Goodnow and Family Scholarship to do so. So that's an awesome accomplishment right there. And now please help me again to welcome Sydney on stage.
Cancer. The word cancer carries an incredible amount of weight with it. It is the name of a medical condition, yes, but it also encompasses the social and emotional toll that the disease carries. I heard about this firsthand when my high school calculus teacher told us about her experience with cancer. She explained how it changed nearly every part of her routine, where she could go, the activities she had the energy to participate in, and even how people perceived her. We hear a lot about cancer in the media: breast cancer, lung cancer, brain cancer, leukemia, lymphoma, usually due to their high mortality rate or the populations they affect. Unfortunately, colorectal cancer is also gaining this reputation as it is becoming more and more common in younger and younger people. I'm sure you've all heard to make sure that you get your colonoscopy at 45, or have had parents or friends go through the grueling process of fasting and drinking all of the liquid the doctor gives you before they go in and look for polyps. While this sounds excruciating, millions of Americans do this every year in the name of preventing cancer. Even with all of these tests and continued advocacy for awareness about colorectal cancer, the rates in America are still rising. In fact, the American Cancer Society now estimates that 1 in 5 adults between the age of 45 and 55 are at risk of developing colorectal cancer. This means that in 2025, 7.5 million Americans are at risk of developing colorectal cancer. This year, 152,000 will be diagnosed with colorectal cancer. 53,000 will die. Each of those 53,000 people has a family, has someone who loves them, has hopes and dreams of their own. With such a large population at risk, it makes sense why there is a growing interest in colorectal cancer research. With that one word, cancer, you can turn someone's entire world upside down. So what does fruit flies have to do with this? Well, this is Drosophila melanogaster, only about 3 millimeters long, and it turns out it has a lot in common with humans when it comes to cells splitting. They carry a lot of the same checkpoints that humans do, and those checkpoints are usually faulty in cancer. Fruit flies also have a much shorter lifespan of only about 3 weeks, which allows us to get more samples and to see tumor growth at a much faster rate than in mice or humans. Finally, fruit flies also have a very similar basic anatomy when it comes to their intestinal tract, which makes them perfect for studying colorectal cancer. You can see here that the small intestine and the large intestine in humans are very similar to the hindgut and midgut in fruit flies, which is where colorectal cancer is usually found. Fruit flies also have a lot of the same mutations that are usually faulty in colorectal cancer, in the most common forms anyway. A mutation is a mistake in the DNA code, and it's something that is usually caught by the cell, by checkpoints in the cell, before it duplicates. Now, if the mutation is in these checkpoints itself, there is nothing to correct these mistakes. My lab theorized that giving 3 specific mutations within these checkpoints simultaneously would give us a better representation of what tumors look like in human colorectal cancer. These mutations are in checkpoints P53, APC, and RASV12. Have you guys ever been to a casino and have walked past the slot machines? I'm going to use them to further explain how these mutations raise your risk of cancer. So think of this $sign as a sign of a mutation or a broken form of the gene. If you have just one of these $signs, your risk for cancer is slightly elevated, but not guaranteed. The more mutations you get, the higher your risk. By the time we get all 3 $signs, in this case, all 3 mutations in one cell, your risk for cancer is high. This is certainly not the type of slot machine you would want to win. Now, this would create tumors that are more difficult to treat, the tumors stick together, and duplicate out of control. In order to build this model, we had to do it from scratch. Luckily, my lab has already built models that have just 1 or 2 mutations before, so we use the same methodology here. We'll take a less than 1 hour old female fruit fly with 1 mutation, breed it with a male fruit fly that has a mutation, and that will give us an offspring that has 2 mutations. We then repeat this process with the missing mutation in the male fruit fly, resulting in a fruit fly that has 3 whole mutations. While this process looks simple, it is the culmination of about 3.5 years of research and from contributions of over 20 researchers, one of whom is also in the audience tonight. Fruit flies also, so now that we've made this mega cancer fruit fly, the trick is keeping it alive long enough to reproduce in order for us to actually dissect the larva and see the tumors we're interested in. In order to do this, luckily, many of these mutations are paired with on switches. These on switches allow us to decide when these really dangerous tumors start to develop. We can do this by raising the temperature for a short period of time in the larvae, which then initiates these really deadly tumors. So, congratulations, you've made it in my lab. Let's see if we can do a dissection together. For reference, this is a needle, and this is what you're going to be trying to dissect with the needle next to it. All right, so here's a fruit fly larva. We're going to take our tweezers, we're going to put it at the head and about 3/4 of the way down in this larva, and the goal is to get a sample that extends from the mouthpiece to the ampulla. We're going to pull on that mouthpiece, bringing out the intestines with it, and hopefully getting a sample that is fully complete and clearing away any of the excess tissue. So hopefully you're left with something like this. Now that we have that completed, we're going to take that sample, put it in a tube, and place it with a primary antibody. This antibody is going to hook onto a slot in the cells of the tumors that we're looking for. Next, after 12 to 24 hours, we're going to then put a secondary antibody in that solution. This secondary antibody will then attach and light up the tumors, which is the whole goal of these antibodies, so we can actually visualize the tumors that we want to see. Now we're going to mount it on a microscope slide and look at it underneath a microscope, in this case, a confocal microscope. This confocal microscope allows us to look at these tumors in 3 dimensions so we can see each individual layer. Let's actually look at some of the samples that my lab has gotten. This is an example of a RAS mutation. So if you remember at the beginning, this is just a 1 mutation fly. You can see the tumors are in green, outlined in pink. They are a little teardrop in shape, but they are distinct from each other and they're not impeding the intestinal tract. But it is tumors. This is the 3-hit, so 3 mutations all together. Again, those tumors are outlined in pink and are in green. You can see here that it encompasses nearly the entire intestinal tract and looks very asymmetrical in shape. Looking at tumors like this in Drosophila while using the same mutations found in common human forms allows us to better understand how these cancers develop in humans before we detect them. My lab is hoping to continue this research with this brand new model, and will hopefully try inhibitors to see if we can shrink these tumors. Isn't it amazing that something so small, and it's usually viewed as a pest, can hold so much hope for colorectal cancer research? So the next time that you go to swat a fruit fly away from your banana, think about the fact that the research with it could save your life. Thank you.